Hi everybody, welcome back to my channel on Feynman integration. As promised, today I will be evaluating this integral. It's the integral from 0 to infinity of cosine x over x to the fourth plus 1 dx. And a few days ago I had offered that up as a challenge to all of you to see if you could solve it using Feynman integration. Pretty sure that could be solved using contour integration as well. I would like to see somebody post a video on how to do that actually, because I can't do it. But anyway, I was able to solve it using Feynman integration. So this is how we're going to start. It's going to start in a very familiar way. We're just going to create a function of t closely resembling our original integral. And it's going to be this, the integral from 0 to infinity of cosine of tx over x to the fourth plus 1 dx. The next step is to find a value that we can plug in for t to make this integral evaluatable, make it easy to evaluate. There isn't one that's going to make it easy, but if you pick t equals 0, if you evaluate f of 0, you will get pi times the square root of 2 over 4. And the integral from 0 to infinity of 1 over x to the fourth plus 1 dx is kind of a famously difficult calculus 2 integral. It's probably offered up as like a bonus question on final exams, but that's what it evaluates to. You can actually, the 1 over x to the fourth plus 1 does have an elementary antiderivative. So you can take the antiderivative and then evaluate it at the bounds. Of course, you'd have to use limits and things like that. But you can solve it with techniques learned in calculus 1 and 2. So I won't be solving it here. That's the answer. If you evaluate f at 0, you get pi square root of 2 over 4. All right, so the next step is we're just going to take a derivative with respect to t using the Leibniz rule for differentiation under the integral sign. And this is what you'll get. And it's pretty clear to see that if you evaluate, this is f prime. If you evaluate f prime at 0, you'll get 0. Now at this point, it might be tempting to try to solve this integral, because you'll notice that x over x to the fourth plus 1, you could actually take that antiderivative pretty easily using the substitution that u is equal to x squared. And then maybe try to do integration by parts on that. I did actually try that. That doesn't work out very nicely, so we actually have to go further with the Feynman integration on this. We need to take another derivative with respect to t. That would give us f double prime of t is equal to the integral from 0 to infinity. And let's see, now we would have negative x squared cosine tx over x to the fourth plus 1 dx. Now, at first, this might seem like it would be very difficult to find a value for t to plug into that to make it nice. Actually, if you pick 0, you'll actually get negative pi square root of 2 over 4. And I'll show you why really quick. All right. So f double prime at 0 is equal to negative pi square root of 2 over 4. And the reason for that is this. If we have the integral from 0 to infinity of 1 over x to the fourth plus 1 dx, and then make the substitution that x is equal to 1 over u, we would get dx equal negative 1 over u squared du. So let's plug that in. This would give us the integral from, let's see, well, if x is 1 over u, then u is 1 over x. So 1 over 0 is infinity. 1 over infinity is 0. We would get 1 over u to the fourth plus 1 times negative 1 over u squared du. Let's distribute this u squared here in the denominator, so we'd get a u squared here and a u squared here. Now we multiply the top and the bottom by u squared. That would give us u squared. This would become a 1. This would become a u to the fourth. And this negative would switch the bounds of integration. So we can see that these two integrals are exactly equal to each other. So if this one evaluates to pi square root of 2 over 4, then the negative of this one, which is what we would have if we plugged in 0 for t here, would give us negative pi square root of 2 over 4. I hope that made sense. Okay, well, still not really going to be able to evaluate this integral very easily, so let's just keep going. Let's make f triple prime of t. All right, that's going to give us f triple prime of t is equal to, well, let's see, we're going to be switching back to positive now because cosine will give us negative sign. That negative would cancel with that, so we'll have the integral from 0 to infinity of, and now it's going to be x cubed. Oh, no, I'm sorry, that's sine. Sine tx over x to the fourth plus 1 dx. And now I'm going to use a familiar trick that I've used in several other videos. I'm going to multiply the top and the bottom by x. And then introduce a plus 1 here, meaning we would actually now have to subtract the integral from 0 to infinity of sine of tx over x times x to the fourth plus 1 dx, right? We started with just x cubed times sine tx over x to the fourth plus 1. Multiply the top and the bottom by x, giving us x to the fourth times sine tx over x times x to the fourth plus 1 dx. Then we introduced this plus 1, which had the effect of adding this over this to the entire integral. Therefore, we have to subtract it off to keep things equivalent. And now, you'll notice something nice. This will cancel with this, and we're just left with the integral from 0 to infinity of sine tx over x, which is famously pi over 2. So we're left with f triple prime of t being equal to pi over 2 minus the integral from 0 to infinity of sine tx over x times x to the 4th plus 1 dx. And now you can see that if we take one more derivative of this thing, we're going to get back our original f of t. And of course, I'm going to write that down for you, but that was the whole point of doing that, was so that we could get back our original f of t in some form and then create a differential equation based on that. All right, so we have this, that's all correct. I'm going to erase this. And we will note that if we plug in f triple prime, if we evaluate f triple prime at 0, we will get pi over 2. Okay. Well, still, that integral, that's not good. So we need to keep going. So let's do it one more time. F quadruple prime of t is going to be equal to, well, let's see, derivative with respect to t of pi over 2 is just 0. So we would get negative integral 0 to infinity of cosine tx over x to the 4th plus 1 dx. But this right here is negative f of t. So I'm going to erase this and just write down what we just found out. Now we have this differential equation. F quadruple prime of t plus f of t is equal to 0. Or actually, I'm going to write it this way. It's equal to negative f prime of t. I'm sorry, negative f of t. Now, if you have not taken differential equations, you still might be able to figure this out by realizing this. It's going to be some form of exponential. I hope you all agree. So an exponential can be in this form. Exponentials are written in this form. Some constant a times e to the, we'll call it little b of x. That's a very general type of exponential. And of course, since we'd be taking derivatives to try to match these up, we can just really get rid of that a, since it can be just added on at the end anyway. So basically, we have this exponential that if we take 4 derivatives of it, we need to get back the negative of the original. Well, what happens when you take derivatives of an exponential is we would recover a factor of b every single time. So if we took 4 derivatives of that with respect to, you know what, this should be a t, I'm sorry, since we're using t up here. So if we took 4 derivatives of this with respect to t, we would end up with b to the 4th times e to the bt. So we need some number b such that if you raise it to the fourth power, you get -1. So this is our general form of our exponential, e to the bt, and we need b to the fourth power to equal -1. Well, -1 can be written as e to the I pi. Taking the fourth root on both sides would give us b being equal to I pi over 4. But that's not it. There's actually, there are more solutions to that. In fact, it can be e to the I pi over 4. It can be, I'm sorry, that's e to the I pi over 4. It can be e to the, let's see, 3 pi I over 4. It can also be e to the 5 pi I over 4, and it can also be e to the 7 pi I over 4. And you can verify that. From the fundamental theorem of algebra, we know that the solution to this there has to be 4 distinct roots, and these are them. Those are the 4 distinct roots. We have e to the I pi over 4, e to the 3 I pi over 4, e to the 5 I pi over 4, and e to the 7 I pi over 4. So our general solution to this differential equation is this. F of t is equal to some constant a times e to the, now b is actually this, don't get that confused. B in this case is e to the I pi over 4 t. See, this constant a comes from the fact that it will be true that taking derivatives of this, basically if this is true, that the fourth derivative with respect to t of e to the I pi over 4 times t is equal to negative f of t, then we can add any constant in front of that we want. And also, we would have this as a solution for b as well, so we need to add some constant b times e to the 3 pi I over 4 times t plus some constant c times e to the 5 pi I over 4 times t plus some constant d. And you can see this is going to get extremely messy very quickly. D times e to the 7 pi I over 4 times t. Okay, there's our general solution to our differential equation. Let me make sure I got that right. Yeah, if I made any silly mistakes, you get the general idea. If I made any silly mistakes, you know what they are. Put them in the comments. But this is the process. This video is about the process of solving it with Feynman integration. It doesn't look like I made any mistakes though, so far. Okay, now, as much as I'd love to take 4 derivatives of this, there's not enough room on the board to do that. The process goes like this. Since we now know that the general solution to that equation up there is this. What we need to do is take, well, first of all, we need to plug in 0 for our t and set it equal to pi times the square root of 2 over 4 to give us equation number 1. Then we'd need to take a derivative and plug in 0 and set it equal to 0 to get us equation number 2. Then we'd need to take another derivative, evaluate it at 0 and set it equal to negative pi square root of 2 over 4. And then finally take another derivative, evaluate it at 0 and set it equal to pi over 2. And that would give us a system of equations that we could solve to find A, B, C, and D. And then from there, we would actually have our f of t. And then we could just plug in 1 for t to get our answer to I. And I'm not going to do all that on the board. If you guys want to go through all that hell and do that, I've already done it once on paper, and I used a calculator to verify it too. Because with a problem this messy, there's so much room for mistakes. There's so many ways you can mess up a sign or write something down incorrectly and then interpret it wrong later. So I'm just going to right now jump to what you would actually get for f of t if you did everything correctly as I've described. So for f quadruple prime of t equals negative f of t, with these conditions, this is what you get for an f of t. F of t will be equal to pi times e to the negative t over 2 times the sine of t over 2. Hold on 1 second. Plus the cosine of t over 2, and then this needs a parentheses around it. And then that is over 2 times the square root of 2. So that's what you get for an f of t given this and all the initial conditions. I just want to check that one more time just to make sure I've not gotten anything wrong. Okay. No? That's it. So now it's a simple matter of plugging in 1 for t. And this is what you'll get. You will finally get that I is equal to pi times, oh, wait a second, there should be square roots t over the square root of 2. So finally, what you get for I is pi times sine square root of 2 over 2 plus cosine square root of 2 over 2 over 2 square root of 2 times e to the square root of 2 over 2. I'm going to verify that. We have pi sine the square root of 2 over 2 plus cosine square root of 2 over 2 over 2 square root of 2 times e to the square root of 2 over 2. That is correct. And I don't know, maybe some of you were able to get that. But in any case, that is the answer to that integral. So, hope you enjoyed that.